All right, let me go ahead and get the lights and whatnot, the TV's booting up. Let me go ahead and get this started. Okay, so you all are collecting homework 2 up there, so I wanted to go ahead and, while that's being done, I wanted to go ahead and talk a little bit about some scheduling. So here's our schedule. Let me zoom. That's good enough. Here's our schedule for the semester, and I usually like to take a little bit of time to just make sure we're still on point with with our schedule and make sure we're still going to make our time. And it looks like everything's going to go pretty well. We are right here. It's the Thursday on week 4, and we're actually well ahead of where I thought I would be. We were supposed to start torsion today, and we've already started it and gotten into it. I'm not going to take the exam and move it up, though. Okay, we're going to keep the exam on the same day. All right. So is everybody okay with that? You all don't have any scheduling conflicts? You don't have 7 exams on the same day? Okay. All right. Let's talk a little bit about the exam, just so everybody's aware. First off, I usually don't like to call them exams. I usually refer to them as celebrations of learning. So we're going to be celebrating on Tuesday, the 27th. I got jokes. All right. I will bring party favors like the exam. There we go. Got some laughs. Okay. So let me sort of tell you how I like to do the exam review and whatnot. So the day before the exam, we will have exam review. We won't lecture anything. Okay. What I'll do is I'll come in and I'll present like a short little PowerPoint, and I'll try and summarize everything that's going to be covered on the exam, and it'll have all the topics, all the formulas, and a nice little, hey, here it is. Okay. What I like to do then on Thursday, on that review day, is I'm only going to talk for about maybe 10 minutes, 10 or 15 minutes. And then the rest of the time is you asking me whatever you want, okay? So, if you want me to work through a problem, if you've got questions about some of the concepts, units, values, life, whatever, okay? Now, you can ask me whatever you want. You can ask me, what's the answer to problem 1? I might not answer it, but I'll do my best to prepare you as well as I can for the exam on Tuesday. All right. As for the exam, what I usually allow is you all can. Oh goodness, what the heck? I'm breaking the table. Okay, that came off. All right. Somebody did not do an appropriate stress analysis on this, little component right here. All right. For the exam, I let you all use, calculators, pencils, all that, and I let you bring a formula sheet, an 8.5 by 11. You can put whatever you want on it, okay, except for one thing, except for worked out problems, okay? And there's a reason for that, and particularly in this class, and even more so in classes like structural analysis, what can happen is you get focused on that one particular problem, and then you're looking at the exam and it's something different, and it sort of throws you for a loop. But you can write equations, you can write procedures, unit conversions, anything you want, okay? And again, I'll provide that PowerPoint that kind of summarizes the broad strokes of what it is that you need to know. All right, sound good? Anybody have any questions so far? Okay, all right. Now, just so everybody's clear, exam 1 is going to be on all the stress strain stuff that was at the very beginning, everything on axially loaded members, and everything on torsion, and that's exam 1, okay? And then exam 2 will be on beams, and exam 3 will be on everything else, okay? Again, I'm not a comprehensive guy, so once we finish exam 1 on axial loads and torsion, you won't see at least the difficult stuff of that on exam 2. I mean, some of this stuff does carry over a little bit, but I'm not a comprehensive guy, okay? Everybody good? Okay. Now, just so everybody's clear then on other bookkeeping issues, now I forgot to print this off, but I am going to assign a homework today on torsion, okay? Now, I'm going to have it due next Thursday, okay? Now, it's only 3 problems. It's not 4, and this is also uploaded on Blackboard, so you all should be able to at least get the problems. But if not, it's just 3 problems, 341, 376, and 3810. Just ignore Part C on 3810. This is how this is going to work, okay? On Thursday, you all are going to turn this in, and then that day, I'm going to give you a solution, okay? Because I don't want to test you on material and you not be prepared, okay? So I'm going to give you a solution. But the caveat is, if I give you a solution on Thursday, I can't accept late work, you know? Like, I can't give you the solution on Thursday and then Friday, oh, well, here you go. You see what I mean? So everybody okay on that? All right. Again, that's sort of my way of ensuring that you're prepared for the exam, but I got to be equitable. All right. So everybody good? Okay. Any questions? All right. I apologize for not having hard copies of this, but I'll have it on Tuesday. So you all will have that. And again, all the problems are on MU Online, and we're recording. So just go to YouTube. All right. Everybody good? Okay. All right. So with that, let's go ahead and get started. I did get the sign-in sheet started, right? Okay. All right. So I'm not going to go through this derivation again. I promise I won't do that to you, but I do want to at least go through the broad strokes. So we're talking about torsion now. And again, the idea is, you're taking a segment and you're twisting it. We talked about the idea that we're only going to reserve our discussion for circular members, shafts, pipes, things like that. Nothing square, nothing triangular. If I give you a torsion problem and it's non-circular, I made a mistake, okay? Now, if you are interested in torsion of non-circular sections, take advanced stress analysis. As far as I know, I'm offering that next semester, so that'll be some good stuff. There's some fun stuff in that class. It's sort of mechanics of deformable bodies 2, if you will. Okay, so we went through our derivation, and I'm going to, skip this or, skim over this very quickly. But a few of the observations that we made were that the deformation and the strains were proportional to the distance from the center. In other words, if I take a circular shaft and I twist it, I don't get any stresses or strains at the dead center. But the farther I get away from the center, the more stresses and strains I develop, okay? So we have a shear stress profile that looks something about like this, linear from the center, zero stress at the center, maximum stress at the edge. And then we use some integration concepts to sort of integrate that stress and ultimately that torque about that cross-section to try and solve for that maximum stress. And after you go through the calculus and plug and chug and do the grunt work, you find that you're isolating a very particular integral by itself. You're isolating this, 2 pi times the integral of rho cubed from 0 to r. Okay? That is a very particular important integral, and it is a particular what we call section property. So the idea is if I take a samurai sword or lightsaber, if you're a sci-fi fan, and I cut through that circular shaft, I'm looking at a circle. There are certain properties of that circle that are important to us as engineers. Things like the area, things like the center of gravity, and also things like J, things like this integral. J for a circle is essentially the same thing as the polar moment of inertia, which is why the book uses I sub P. I like to use J because it differentiates between pure torsion and that warping aspect that we mentioned later. So, and plus J's less letters than I sub P. So I tend to be lazy, when I can be. Okay, so the nice thing about it is they're very easy plug and chug expressions. So this is J for a solid shaft. This is J for a pipe. Similar to how you compute area, you just sort of, like if you've got a pipe, you take J for the large section minus J for the small section, and you get J of that ring, that pipe. So going through and doing some plug and chug, and I'm going to skip over this kind of quickly, we're able to obtain a summary of torsion formulas that we're going to be able to use in our assessments. So shear stress is T rho over J, and then the maximum stress is obviously at the edge, TR over J. We've got shear strain, which we just take that and divide it by G. G is that shear modulus, just like E is that axial, Young's modulus. We've got our angle of twist, J formulas for shafts and pipes. And then if we've got a constant T and a constant J, we can just plug and chug. Okay? Make sense? Last thing, remember your relationship between E, Poisson's ratio, and then the shear modulus G. And then we did this example, we did this one, and we hadn't quite gotten to this one. So did anybody have any questions about this example? If I remember correctly, we were kind of, you know, we finished it like just in the nick of time. So is everybody good on this? Okay. So I got another one for you, somewhat similar. So let me move some of this stuff out of here. All right. Okay, give me a moment. Let me get all this stuff up here organized so I'm not creating a complete mess. Okay. So you'll notice some of this stuff probably has a little bit more of a mechanical flavor than civil flavor, but it just sort of is the nature of the beast when it comes to torsion. So I've got a circular pipe, and it's subjected to a series of torques. Now, one of the things you'll notice is if you look at the torques, okay, so I've got T1 and T3, or T sub 1, T sub 3 acting this way, and then T sub 2 acting that way, okay? So you'll notice that's why it says the torque is given by gear C, because T2 is, you know, supplying torque in this direction, and gears B and D are resisting it in the opposite direction. But look at the numbers. You know, I've got T2, which is 450 Newton meters, going in this direction, and then 275 and 175 going in this direction. So if you sum torques, I got 450 going this way. I got 275 plus 175 going in the opposite direction, so everything meets equilibrium. That make sense? That's just, you know, I just wanted to throw that out there so that everybody's clear. Okay, now this shaft the segment that's resisting this torque is not a shaft, it's a pipe, okay? So I want to be clear, I'm using that. So the outer diameter is 40 millimeters, the wall thickness is 5 millimeters, okay? So that we got to be clear here in a little bit when we calculate our dimensions and ultimately calculate J. Now we've got the lengths, we've got shear modulus, and we've got two tasks. We need to determine the maximum shear stress in each part, and then we need to determine the angle of twist between gears B and D, okay? Does that make sense? Everybody good? All right, so let's see if we can start listing some properties and being clear on some of this. Let me get some of this out of the way. I keep moving stuff around, but it'll be all right. All right. There we go. Okay. All right. So the first thing I want to do is, okay, we're going to look at some given parameters. And the first thing I want to look at is that pipe. Okay? Now, let me go back to this. Wait, oh, wrong one. Let me go back to this. Okay, so let's read what it says. Okay, so I have an outer diameter of 40 millimeters, and I have a wall thickness of 5 millimeters. Okay? All right. Now, maybe what I ought to do right off the bat is, let's just sort of choose something right off the bat. I'm going to choose that my forces, bless you, are ultimately going to be in kilonewtons, and my lengths are going to be in millimeters. Okay? Just to sort of have that right off the bat, just so we can be clear. I mean, I'm usually a U.S. units guy, so it just sort of helps me out. I mean, a lot of the stuff we've done in the U.S. units, I think we've reserved ourselves mostly to kips and inches. So I just wanted to have set that right off the bat. Okay. Now for this pipe, we know that the outer diameter is what, 40 millimeters? And the the thickness, I'm getting ahead of myself, the thickness is 5 millimeters, the wall thickness. So help me out. What's the inner diameter? 30. It's 30. Now, if that's unclear, let's take a look at this. So here's the pipe. Okay, and I'll sort of shade that in a little bit. So there's the pipe. Those are the best circles you're going to get me to draw. Okay, so this outer dimension that we see right here, this is 40 millimeters, right? Okay, now this wall thickness right here, this is 5. So how do I get from here to here? Well, I take 40, and I've got to subtract one on the right and one on the left, right? I got to take 2 wall thicknesses off. So that means this is 30 millimeters. So DI is DO minus 2T, which is 30 millimeters. Make sense? Not too bad, right? All right. If I'm given that, I can go ahead and compute J. Okay? Now, J is, for a pipe, pi over 32 times d naught to the 4th minus di to the 4th. Make sense? So that is pi over 32, 40 millimeters to the 4th minus, oh, pen got away from me there, 30 millimeters to the 4th. And so what do we get right here? There we go. All right. So 171,805, and it's like what, 0.8? There we go. All right. So millimeters to the 4th. All right. So far, so good. All right. Now I wanted right off the bat to put these units down because I wanted to show you something that you might not remember, but that's all right. So I want to look at G. Okay. So our given parameter, we know that G is, was it 80 gigapascals? Is that what it was, 80? Well, the nice thing about the units is that if I take a kilonewton and I divide it by a millimeter squared, I get a gigapascal. So I don't need to convert anything at all, okay? See, a newton per meter squared is a pascal, okay? Well, if I'm multiplying by 1,000 and then dividing by 0.001 squared, go through and do all the math, that turns into that giga prefix. All right, sound good? Everybody okay with that? Yep. You got 10 to the 9? Yeah, because mega is 10 to the 6th. Yeah, I always think about it like computers. You know, kilobyte, megabyte, gigabyte. Make sense? Everybody good? Cool. All right. Now, let's also write these lengths. So the lengths, we've got length BC, which is what? Was that 500 millimeters? And length CD, which is 400 millimeters. All right. So far, so good? Okay. Now, let's also look at these torques. There's also another nifty component about torques before we begin. Note, I propose to you that a Newton meter is the same thing as a kilonewton millimeter. It's the same thing. Now, how am I getting that? Well, that K, I mean, when you see K, basically you're just multiplying by 1,000. So if I multiply by 1,000, or 10 to the 3rd, and then multiply by that M, which is basically dividing by 1,000, I mean, what's 10 to the 3rd times 10 to the minus 3rd? Just cancels out. It's just 1. So a Newton meter and a kilonewton millimeter are the same thing. Yes, sir?
Well, the gigapascals, how did you get 10 to the 9?
Okay, because what I'm doing is this. So watch this. So I've got 10 to the third times newtons, right? And I've got 10 to the minus third times meters, right? Squared. So that's going to be 10 to the third newtons over 10 to the minus 6 meters squared. So 10 to the ninth Newton per meter squared. Because when you divide, remember you subtract the exponents, so it's 3 minus negative 6 or 3 plus 6. That's 9. That's a good question. All right. Everybody good? All right. All right. So far, so good? All right. I'm going to run out of room here, so I'm going to go ahead and go on to the next panel. Everybody good? All right. Okay. All right. So let's look at these torques. Now, what I'm doing is I'm wanting to determine the torque inside each component of this bar. So, I mean, what's the bar look like? It's kind of like this, kind of like that. So if we want, let's see, let's call this A, B, C, D, E, okay? And let me, give me a moment. Let me go ahead and pull the image up. Oh, wow, that is much larger than I thought it would be. Okay. So using our right-hand rule, remember that right-hand rule? Okay, so torque 1 is sort of going like this, right? T1. So it's sort of like, let's see, right here, and it's going like that, along the shaft, right? Make sense? And so this is T1, and what's the magnitude? What's that, like 275? Kilonewton millimeters, right? Because that's what's going on there. Now, T2 is going in the opposite direction, like that. Right? So that's T2, and that's 450. Oh, getting ahead of myself. And then this one's going like that. So T3 is, was it, oh, no, it's 175, right? Okay. Does everybody see how I'm doing that? I just want to make sure you all are understanding the sign convention. So far, so good? Now, let's just be clear on our goal here so that we understand why I drew all of that. Let's look at, for instance, segment BC. We know the length of that segment, we know the G for that segment, and we know the J for that segment. And same thing with CD. We know how long it is, we know the G, and we know the J. What we don't know are the torques, okay? So what I'm going to do is I'm going to cut a section, and I'm going to look to the left or look to the right, okay? So in other words, let's cut a section between B and C, and let's look to the left. So let's do this. Let's cut a section, all right? So, and I'm also going to cut another section right here. So let's look at, maybe I'll number them. Section 1, Section 2. Yes?
T1, if you go like, use the right-hand roll, is it pointing to the right? Follow it like this.
Oh, I did that backwards, didn't I? So, oh, they're all backwards. Whoops. It's me going like this, back and forward. So they're all backwards, actually. Whoops. All right. down to 4 mistakes, I think, right? So that one's, yeah, that one's going like this. This one, yep, going like that. And this one's going like this. Make sense? So far, so good? All right. So let's look at this first section. All right, so I've got T1 is 275 kilonewton millimeters. And here's where I cut the section. Now that torque is acting like this, right? So far, so good? Yep. So what that means is that inside this segment, I got to have a torque acting in the opposite direction, right? Make sense? So I'm going to call this torque BC. Make sense? And if I just think about it like it's sum of forces. If I sum torques and say the sum of torques has to equal 0, I get that TBC is 275 kilonewton millimeters acting like that. Make sense? So far, so good? In other words, the torque, the shaft, or no, in this case the pipe, because it's a pipe, it responds by developing a torque in the opposite direction. Make sense? Not too bad, right? Okay. Now, oh, goodness, this thing's getting tangled. Now, for the next one, I'm cutting this section like so, and I've got, what do I have? I've got T1 is 275 kilonewton millimeters acting like that, right? Make sense? But I've also got, at point C, a torque going like this. Right? So think about it like this. If I've got 450 kilonewton millimeters going this way, and I've only got 275 going this way, I need a torque acting in the opposite direction. What's that? No. Well, think about it like this. Imagine if they were forces and not torques. Imagine if I had 450 pounds pulling to the left, and I only had 275 pulling to the right. I need an extra how much going to the right? 175. See what I mean? So that the torque's going, think about it like it's forces, because it's basically the same thing. If I've got, 450 going to the left, I've got to have 450 going to the right. In this case, we're not dealing with forces, we're dealing with, twisting it, but basically we're saying the amount twisting it this way has to equal the same amount twisting it that way. Same concept. Make sense? Everybody okay? All right. So if I sum torque, so we'll call this TCD, and I sum torques. If you want, you can do it like this. Sum torque equals 0, and you can say I've got that, and I've got that, and what do I have? I've got T2 is 450, and then I've got T1 is 275. Oh, getting ahead of myself again. And then TCD, I'm going to have 450 equals TCD plus 275. So therefore, TCD is 175, and it's acting like that. Make sense? So my point is that within segment BC, I'm going to get some rotation, and within segment CD, I'm going to get some rotation. The point is that BC is going to rotate one way, CD is going to rotate the other way. So I'm going to take those rotations, I'm not going to add them up, I'm going to subtract them. Does that make sense? Okay.
So is that like an internal bending moment?
Yeah, but it's bending along the axis. Okay? It's along the, it's a moment, but it's along the axis. It's axial. Not like this. Like that. But yeah, it is a moment. Make sense? Okay, all right. Everybody good? Okay, so now what we're going to do is we're just going to take care of this directly. Let me start off with the rotation first, because I think that this is going to be the most straightforward. Let's start off with the rotation, or the angle of twist. All right. Here's this. Okay. Now, ultimately, what we're trying to find is the angle of twist between point B and point D. Okay? I propose to you that to get the angle of twist between those 2 points, all we have to do is just sum up along the length. In other words, I propose that we take the angle of twist between B and C, and then add to that the angle of twist between C and D. Does that make sense? That if I get the angle of twist from here to here, and then the angle of twist from here to here, I get the angle of twist between the whole thing. Make sense? Okay. All right. So how do I get the angle of twist? Well, I mean, how do I get it in general? I have constant torques within each of those segments, and I have constant J for each of those segments, right? So if I got that, it's TL over GJ, right? No integration. So let's take each of these one at a time. All right? Let's take BC. What is the torque inside BC? There we go. 275 kilonewton millimeters, right? What is the length of segment BC? There you go, 500 or LBC, which was 500 millimeters. So if you want, I can say, all right, this is, oh goodness, I'm losing some. This is TBC, this is LBC, right? Okay, what's G? And then what's J? Well, that's the one we computed. That was like the 171,805.8 millimeters to the fourth. Now, what I'm going to go ahead and do is this. Now, which way was that torque acting? It was acting like that, right? So I propose that that angle needs to be expressed. I'm going to include that sign in that fashion, just so I'm not confused about the sign convention. Make sense? Okay. So that's that angle of rotation. Now let's do this. All right? So maybe I'll do G, J. Okay. So what do we got? Okay, so we need TCD, which is what? 175? LCD, that's TCD. Then we need LCD. And what is LCD? And then it's the same GJ, right? So 80 gigapascals, and then millimeters to the fourth. So G, J. Now, just so I'm clear on signs, this one was acting that way, right? Make sense? All right, so let's take each bracket one at a time. And let's do it to 4 decimal places. Now keep in mind, these are rotations, so they will come out small. What will the units be if I plug and chug these numbers into the calculator? It's a rotation. Okay, all right. If the unit, all right, keep in mind, everything's kilonewtons and everything, it's unitless, right? And when you express an angle without units, what are you expressing it in? Radians, okay? So this is, whatever we get is going to come out in radians. Now, if it's still a little iffy, you can go through and do a unit analysis here on the bottom and say, all right, on the top, I've got kilonewtons times millimeters over gigapascals, which is kilonewtons per millimeter squared, times millimeters to the 4th. So on the top, I've got kilonewtons times millimeters squared, and on the bottom, I've got kilonewtons times, I've got millimeters to the 4th over millimeters squared, it's millimeters squared. So there are no units, okay? But when you express an angle without units, you're expressing it in radians, okay? So do that math and tell me what you get. Give it to me in 4 decimal places, let's say, just so we're clear. No, don't do that just yet. Just each fraction. For the first one? Now this is a decimal on the 0.8. That might have changed things. There's a decimal right here. Because yeah, I got 0.100 radians. Maybe it was that decimal right here. Yeah. And that's going in this direction, right? Plus this. Now what do we got over here? So, like that. Anybody else getting that? Okay, all right. And that goes this way, right? So think, if I've got 0.01 rotating in this direction, but I've only got 0.0051 this way, my net rotation is in this direction, and it's the difference, right? So, let me, here, I don't want to erase that. I'm going to move that. Move that over here. So what's the difference? Comes out to be what? 0.0049 radians that way. Now, I don't like radians. I can't think in radians. I think in degrees. How do I convert that to degrees? Or the 360 and 2 pi or 180 over pi, whichever you want. But recognize that 180 degrees is the same thing as pi radians. Or you can use 360 and 2 pi, that's fine. I think a lot of times 360 and 2 pi is sort of what you remember, and that's okay. But you put that on the bottom, the radians on the bottom, because you want radians to cancel and you want to get degrees. Plug and chug, and that'll give you 0.281 degrees in that direction. I'll put that that's the angle of rotation between B and D. And there you go. All right. And I want you to behaviorally think about this a little bit. The rotation in segment 1 or segment BC was larger. And that kind of makes sense if you think about it. Remember, BC had more torque, right? BC had 275, CD only had 175. That's number 1. Number 2, segment BC was longer. right? It was a longer segment. So because it's a longer segment and it has more torque, it's going to rotate more, okay? Because again, the angle of twist is a function of its length. The longer it is, the more it's going to rotate, okay? All right, that makes sense? Okay. Now, one of the other things that this problem asked was for the maximum shear stress, okay? Now, when it comes to maximum shear stress, the pipe is the same size on C and D. So let's go back to this. How do we calculate maximum shear stress? What's the formula for maximum shear stress? TR over J, right? So the J is the same on both shafts, and the R is the same on both. And I keep saying shafts. This one's a pipe. It's a pipe segment. So really, to get the maximum shear stress, all we need is the pipe with the maximum torque. And which is that, BC or CD? Which one has more torque inside it? BC, right? Because look right here. All right, BC has a torque of 275. CD has a torque of 175. So the maximum shear stress is going to occur inside segment CD. And that's all there is to it. So I'm going to go ahead and go on to the next panel. Everybody got this? All right. So max shear stress. All right, so how do we get that? Well, we recognize that that's going to be in segment BC just because segment BC has the larger torque. All right, excuse me, sorry. Now we know that the outer diameter is 40 millimeters, so the radius is 20 millimeters. And J is that 171,805.8 millimeters to the fourth. So tau max, bless you, tau max is TR, bless you, over J, which is, oh, I didn't put the number, 275. I just wrote the units. All right, so 275 kilonewton millimeters times 20 millimeters over 171,805.8 millimeters to the fourth. And we get a tau max of what? It might seem like a small number, and that's okay. 0.032. Now, let's see, what are the units for that? Kilonewton per millimeter squared. And what is a kilonewton per millimeter squared? Gigapascal, okay? So if I want, I could say this is 0.032 gigapascals, or if I want a more usable unit, I might say or 32 megapascals. Not too bad, right? It's not too bad, right? All right. Keep in mind the big picture, the point. What you would then probably do is say, well, let's say this shaft is made out of, or this pipe is made out of titanium, aluminum, whatever. You would then say, okay, let's say it's made out of aluminum. For aluminum, what is the maximum allowable shear stress, and see whether or not this is an acceptable design. If not, either change your material, change your wall thickness, whatever you need to do to improve its behavior. Make sense? Any questions? Okay. Let's see where we're at. Oh, we're doing good. Okay. Any questions? All right. Now, this is about as mechanical engineering a topic as I can cover. So let's talk a little bit about power-torque relationships. So what we're going to do is look at the relationship between supplied torque in a torsionally loaded shaft or a torsionally loaded pipe and resulting power. Okay? So I'm going to break it back to physics, to something that I think you've seen before. Let's go back to try and define what power is. And I think the easiest place to start is to start with work. Okay? So it's one of the fundamental concepts that you learn in physics. And what is work? It is a force acting over a given distance, right? So you define work as force times distance, okay? Now that's linear. That's, taking a force and going through a distance. You can also define work as torque going through a given angle, okay? So if you have force going over a given distance or acting through a given distance, or torque acting through a given angle, that's work, okay? So that's work. Now what's power, okay? Power is the rate at which work is done. So rate, that's rate of change, i.e. derivatives, right? So power is the rate at which work is done. So the derivative of work with respect to time. Make sense? Okay? So, excuse me. All right? So I can say, okay, well, what's dW dt? Well, work is torque acting through a given angle. I can say, well, if I've got a constant torque, it's basically the torque times the speed of rotation, okay? And speed of rotation, while that might be an odd term, is probably something you've heard before. I mean, you drive your car, you look at the odometer, and it expresses how fast your engine is running in revolutions per minute, right? RPMs. What is that? It's angular speed, right? Revolutions per time. Make sense? Okay. So, in other words, this is angular speed, torque times, we call that omega, all right? So if we want to express that from a frequency standpoint, cycles per second, we have to turn that angular speed into a cyclic speed, so we would just convert that with 2 pi. Make sense? The number of revolutions, all right? So far, so good? Okay. All right. Excuse me. All right. So what I've got here is a relationship where I'm taking applied torque versus frequency, revolutions per second. This is sort of my power-torque relationship. Now, if my base unit of time is in seconds and I want to convert this into revolutions per minute, I've got to include a 60 in there as well. Obviously, 60 seconds in a minute. So this is a power-torque relationship that would relate the number of revolutions per minute, this N, and 60, so applied torque and resulting power in terms of revolutions per minute. So far, so good? Pretty straightforward, okay? What gets funky are some of your unit conversions in regards to power. So let's look at some of the units in US units and in SI units. So if I'm looking in US units, a very common expression for torque is foot-pounds, okay? So you would think that the resulting power would be foot-pounds per second, okay? In US units, you don't really hear much about power in foot-pounds per second, but a very common expression for power is horsepower, right? Everybody heard the term horsepower, right? Okay. Well, 1 horsepower is 550 foot-pounds per second, okay? So go through and do the unit conversion, and what I tried to do was come up with a nice, pretty plug-and-chug expression for you. So in this box, what you would do is if you take a torque in foot-pounds, okay, and multiply it by the following expression where N is your RPMs, your revolutions per minute, that will generate a power that is in horsepower. And how do I get that? I take my original expression and recognize that 1 horsepower is 550 foot-pounds, and then on the bottom, well, what's 60 times 550? There you go. Make sense? Okay, so that's just a nice, pretty plug-and-chug expression for U.S. units. For SI units, there's really no, it's pretty straightforward. It just comes out in watts, and that's sort of all there is to it. So it's pretty straightforward. The complex component is really the U.S. units. I'm a U.S. units guy, but I'll be the first person to admit that our unit system is a little funky from time to time. I'll be the first person to admit it. But I'm stuck in my ways. I can't change. I'm sorry. Sorry to all you mechanical folks, but I think in horsepower, and I think a lot of people do too. All right, so I think you'll see here in a second how this really isn't too bad, but this has some very significant practical applications. So let's look at this example. So we've got a motor driving a solid circular steel shaft that's transmitting 30 horsepower to a gear. Okay. So because it's steel, I went ahead and provided the G value, the shear modulus for steel. So we've got this motor submitting this power. The allowable shear stress in the steel is 6,000 psi. So this is a little bit of a design question. I'm saying for steel, here's the maximum stress we're allowed to generate. Now the length of the shaft is 10 feet long, and now we're actually going to look at this from a design standpoint. Okay? I want to determine what's the required diameter of the shaft if it's going to be operated at 100 RPM, and what's the required diameter to limit its angle of twist. Now I've picked this 5.73 degrees. That would come from either some fabrication specification or some code requirements for engines or what have you, just something like that. Or maybe just from the engineer who's saying, I'm limiting that angle of twist to that much, and you've got to design accordingly. All right. Anybody have any questions? Well, okay. So what that's indicating is that you're supplying torque. It is resisting torque in the opposite direction. That's what that's saying. All right. Sound good? All right. So you're supplying this torque, and yeah, it's moving. But if I know it can be a little tough to think about this with torsion, but it's kind of the same idea with the rope trick. If I'm pulling 20 pounds this way, you're going to be resisting in that direction. If I take a shaft and twist it this way, it responds by developing a torque in the opposite direction. Make sense? With torque, it's a little tough to visualize that sometimes. So that's why I try and think of it in those arrows, just that way and that way, because it's really basically the same thing. All right. So far, so good? All right. Let's see. I think we can knock this one out. Let's see. Okay. So now we're kind of in a design question, kind of. All right. So what do we got? We've got given parameters. All right. So we got a power was given as 30 horsepower. All right. We've got a tau max of 6,000 psi. All right. We've got a length that's 10 feet. And I'm going to go ahead and just say, you know what, 120 inches. I've got a G value that's 12 times 10 to the 6 psi. Okay? So maybe if I wanted, I could do like I did on the last problem and say my forces are going to be in pounds and my lengths are going to be in inches. If you want to just do that right off the bat. That's not actually a bad way to go about some of these problems, just so you know when you input values into an expression that everything's consistent. Just sort of that mental reminder, okay, make sure I'm converting everything. Now, what I'm going to use is I'm going to use that relationship I derived a little bit ago that says, oh, I don't know why that didn't want to write, that my power in terms of horsepower is essentially my torque in terms of foot-pounds times the following conversion, 2 pi n divided by 33,000. Now, this n, I'll say for part A, we were given an angular speed of 100 RPM, 100 revolutions per minute. Okay? Make sense? Okay. All right. So what I'm going to do is this. Foot-pounds. Sorry, I left that off. Foot-pounds. Okay? So if I look at this expression and I say, all right, I've got a power in terms of horsepower, I know the angular speed. Since I'm in design phase, what I really need to know is I need to know the forces inside that shaft. If I know the forces inside that shaft, I can then determine, well, what's the required diameter of that shaft. Now, since we're dealing with torsion, it's not forces, it's torques. So if I've got this expression, I need to take this expression and solve for the torque, right? So I've got power, I've got the number of cycles. I propose that to calculate the torque in foot-pounds, it's going to be the power in horsepower times 2 pi n. Literally just flip and multiply. Bless you. All right. So far, so good? All right. So what do I got? I got 30 horsepower, 33,000, 2 pi times 100 RPM. What does that come out to be? There we go. Yeah, so 1575.6 foot-pounds. And this is where you can kind of put your units blinders on, because you know if you got your correct input, you're going to get your correct output. Now this is in foot-pounds, so I'm going to go ahead and convert that to inch-pounds. So am I going to multiply or divide? Multiply. So that's 18,907. Oh, 90, not 00. 907.6, yeah, inch-pounds. .2? Okay. It's rounding, you know. It's not going to appreciably change anything. Yes, sir?
You don't have to change RPMs to radians.
Well, that's where the 2 pi comes from. So a couple things. So radians per second is converted to revolutions per second through that 2 pi. Okay? Revolutions per second is converted into revolutions per minute through that use of that 60. Okay, that's a good question. The 60 is built into that 33,000 right here. That's where the 60, and then 60 times 550. No, that's fine. This is good stuff. All right. Sound good? Is everybody else clear on that? Because I know we're kind of putting our blinders on a little bit with the units conversion, so that's fine. I mean, that's completely fair to ask that. All right. So far, so good? Okay. So now we know the torque that has been supplied to this section. Okay? We know the torque. The torque that goes into this section is about 19,000 inch-pounds. Okay? Now, what do we know about this shaft? Okay? We know the torque going into it. We know that the material it's made of. So because we know the material, we know its allowable stress, right? So let's think in terms of stress. If I've got a torque, ignore the section properties for a second. If I got a torque and I'm applying it to a section, how do I get the maximum stress? We just used that a second ago. TR over J, right? Make sense? So let's just think about that. Tau max is TR over J. So far, so good? Now, we're in design phase, so we don't know a couple things. There's a couple things we don't know. We don't know the R or the J, right? But they're related. Okay, let's do a little bit of algebra here. Okay, I don't like dealing with fractions, so I'm going to move this over to the left, and I'm going to say tau max times J equals TR. All right. So far, so good? Okay. Now, you're going to see what I'm going to do here in a second, and I think it'll make sense. How do we calculate J for a solid circular shaft? Pi d to the fourth, right? D to the fourth over 32 equals T times R. And what's R? Well, we don't know it, but we could say it's D over 2, right? Make sense? Okay, I want to pay attention to this expression real quick. Let's look at that. What do we know going into that equation right now? Well, we know the torque, right? We know the torque, 18,907. Now, we don't know tau max, but what is the maximum allowable stress? 6,000 psi. So maybe if I plug in a maximum stress of 6,000 psi and a subjected torque of 18,907, maybe I can then solve for the diameter. In other words, I am determining what diameter is required to achieve a stress of 6,000 psi. Make sense? That's the design part. I'm solving for the diameter. I'm asking, here's the torque going into it. Here's the allowable stress. What's my required diameter? There's the design. Make sense? So let's solve this expression for the diameter. Okay? So anybody see something I can do real quickly right off the bat? D on each side, tau max times pi d to the third over 32 equals T over 2, right? So far, so good? Now, let's isolate d to the third. Okay, so how do I get that? Well, I got T over 2, and I need to flip and multiply, right? So what do I need to flip and multiply? Well, I need to flip and multiply what? 32 over pi, and then 1 over tau max. Does everybody see that? So I'm getting that. So what is that? 32 over pi tau max. Everybody seeing that? All right. You all get that written down. I don't want to squunch this, so I'm probably going to go on to the next panel. Everybody got this? So before I do, what's going to happen to the 32 and 2? They're going to cancel out, right? Or cancel and become 16, right? All right, so continue. So I propose that d cubed is what? What we got? 16t over pi tau max. Is that right? Did I forget anything? There we go. So what is that? 16 times, what's the torque again? Was it 18,000? And then that's pi times 6,000 psi. What's that going to give us? $16.04. And what's our units going to be? Think about what we just solved for. What did we solve for? D cubed. Inches to the third. And if you need, look here on the bottom. I've got inch pounds divided by pounds per inches squared. So that's inch pounds times inches squared per pound, right? Flip and multiply. What happens? Pounds cancel, and I got inches to the third. Make sense? Again, be cognizant of that. All right, here, I'll even move this over here. All right. So if I got d cubed, how am I going to get d? Cube root 16.04 inches to the third, and I get d is what? 2.52 inches. Whoop. I wrote it down right. So there's your answer. In other words, if you're the engineer in charge of designing this shaft, you will specify that that shaft has to be at least 2.52 inches in diameter to safely resist that applied torque. What's that? Well, I mean, maybe not necessarily. Depending on your factor of safety, you might go 2.75 or 2 5/8. You know, it depends on. It also might depend on, was there a factor of safety built into that tau allowable? You know, maybe so. You know, so just depends on what you're. And all, I mean, there's a little bit of what your specification dictates. I mean, I know in the world of structural engineering, a lot of our factors of safeties are given to us. You know, you will use a resistance factor of 0.9. You use it. So it just depends on what you're doing. All right? Make sense? All right, so that's part A. Let's see, part B. Do we have time? Yeah, I think we can knock that out. All right. Part B is very similar. Now, part B, what we were given was a phi max of what? 5.73 degrees. Anybody see a problem with that? We're going to need to plug in radians for what comes up. All right. All right. So what is that? So well, hold on. How do I do that? Well, I need radians. So I need radians up top. And if you want, you can do 2 pi over 360 degrees or pi over 180. It doesn't matter. I'm lazy, so I use pi over 180. It's less buttons on the calculator. 0.1 even. Kind of funny how I suggested 5.73 degrees, right? Kind of funny how that works, isn't it? That wasn't intentional. No. All right. Now, how do I calculate? Let's go back to our fundamental expression. If I've got an angle of rotation, I mean, how do I compute that for a shaft? With constant T and constant J. There we go. TL over GJ. All right. Now we're back in design phase. So what do we know? Well, we know G, right? We know L. We know how long the member is. We know the torque because we figured that out based on 100 revolutions per minute. We know that torque is, what was it, like 18,900 and whatever. So we know T, we know L, we know G. We're back in design phase, so what we don't know are the section properties. We don't know J. J we don't know because we're trying to figure out what is our required J. What is the required section properties for this shaft to safely resist these loads? Now, last time we were looking at a maximum stress. Here we're looking at a maximum deformation. So really what we need to solve for is J. Now to solve for J in this expression, I just need to do a switcheroo, right? Just multiply the J, divide the phi, or phi. What's that? Well, if I multiply this, I'm going to have J phi equals TL over G, and then just divide by the phi on both sides. See what I mean? So TL over G phi. Make sense? Ooh, J is TL G phi. I'm probably going to run out of room on this. I might be writing this out quite a bit. Okay. So what do we got? Well, T is that 18,907.2? What's the length? 120 inches. All right, G is 12 times 10 to the 6 psi, and this is 0.1 radians. And what do we get? Well, inches to the fourth, that is correct on the units. Because remember, we're solving for a J. So it should be inches to the fourth. And if you're still unsure, do the units analysis, right? 1.89. Actually, I can do it better now. 1.89. Everybody else get that? Okay, all right. Now, so that'll tell us what the required J is, but that doesn't really help us out in terms of design. We need to know what the required diameter is. So how do you relate J to the diameter? Well, J is pi d to the fourth over 32. So how do I solve for d? Well, d, what do? I say 32 j over pi, and then what do I do to that whole thing? Raise it to the fourth power or fourth root, however you want to say it. So 32 times 1.89 inches to the fourth divided by pi, and I'm raising all of that to the 1/4 power. So what do I get? .09. Everybody else is getting 2.09. Nope. All right. So think, if you were the designer, okay, and you had both requirements to meet, you could not violate 6,000 psi on your shear stress, or you could not exceed that rotation. Which diameter would you use, the 2.09 or the 2.52? 2.52, because you know, see, if you used a 2.09 inch diameter, you wouldn't violate your rotation requirements, but you generate a heck of a lot more stress than 6,000 psi. This, you know, will safely resist the stresses and is big enough to adequately resist those rotations. Does that make sense? Okay. All right. So real quick, a couple things. Next time in Engineering 216. All right. So what we're going to do next time is, like with axially loaded members, remember how we had internally and externally indeterminate bars or columns? Remember that? Well, we're going to have indeterminate torsional shafts. So we'll have a problem like we did with columns, where remember we had that composite column. It was like a 2-inch diameter brass core and a 4-inch diameter aluminum sleeve around that. We're going to do something similar with the torsional shaft. It's going to be a 2-inch diameter solid aluminum shaft surrounded by steel. Now, just real quick, on the composite axial members, we solved that by recognizing the amount of deformation was the same, right? With this, it's not going to be the amount of deformation that's the same, but it's going to be the angle of twist that's the same. So this problem's going to be real similar to the one we did last time. This one is kind of like the problem that we did, or that y'all had on your homework, where, remember, you assumed that support A was gone, allowed it to stretch, and then determined what is the required stretch to bring it back. Well, this is going to be the same thing, but in rotations. Assume support A is gone, allow it to rotate, and figure out what it takes to bring it back. And then that's everything with torsion and everything on exam 1, okay? Past that, we get into the world of beams, and we start off with areas, centroids, moments of inertia. Some of this you've seen before, some of it's going to be new, and also I'm going to show you how to do it my way, so it'll be a little different. That's all I've got. If you haven't turned in your homework, again, pile up top. As for homework 3, again, I forgot to bring the hard copy, but it's on MU Online. It's also in the video. I'll bring hard copies on Tuesday, and that's due on Thursday. Can't accept late copies because I'm giving you the solution that day. That's all I got. I will see you all next time. hold on for one sec. Let me stop this or I'll forget.